Today I am going to give video recording on the uncovered syllabus. I think all of you want to be fine because all are locked in home due to COVID-19, but government has guided us to cover uncovered syllabus by online. But the thing is, most of the students are not coming online due to unavailability of internet or non-availability of a smartphone. So in order to make to video online is not possible. That's why I am going to recording the video and I will upload it to YouTube or I will send it to your group. And today I am going to take a discussion on the solid state chemistry. In solid state chemistry, I covered most of the syllabus, but I left with only two important subtopics, that is a derivation of Bragg's law and the structure of sodium chloride. Now today I am going to start the Bragg's law derivation. Before going to the derivation, let us have the statement of the Bragg's law. What the statement says now, the path difference is an integral multiple of wavelength. Mathematically, we can write it as 2d sine theta is equal to n lambda, where d is a path difference or interplanar distance, theta is the angle of reflection or angle of refraction, reflection or angle of incident, lambda is the wavelength, and n is the art of diffraction. And before going to derivation, let me have some explanation for this Bragg's derivation. See, when a beam of X-ray is passed through a crystal and the impression is taken on the photographic plate, a pattern called diffraction pattern is obtained. By using this pattern, Bragg's invested the structure of crystal of NaCl or KCl. Bragg devised a spectrometer for the measurement of intensity of X-ray beam. The diffraction pattern has produced can be used to study the crystal structure. The Bragg's method for the study of internal structure of the crystal is based on Bragg's equation, which may be derived as follows. Now, when you consider a crystal, it may be considered to be made up of number of parallel equidistant atomic planes as represented by the lines L1, L1 and L2 and so on. Suppose a beam of X-ray is incident on the crystal at an angle of theta. A part of this beam, this AO, is reflected at a point O along the path OC, full point. On the other hand, some rays like BY penetrate into the crystal are reflected by the atom in the atomic plane L1 and L2 as shown in figure. As compared to the ray AO, a ray like BO has to travel a longer distance equal to x, y, z in order to emerge out of the crystal, where OX and OZ are perpendicular drawn on the lines BY and YD respectively. The reflected beam like OC and YD then undergo interference with each other. The reflected rays OC and YD may be in phase. The extra distance XYZ traverse by the ray by should be an integral multiple of wavelength of lambda of the ray. Now let us consider an angle that is a XOY and ZOY, both are equal to theta. So here we have AO, this is AO is equal to BX, then OC is equal to DZ at ZD. Now the path difference is equal to XY plus YZ. This is a XY plus YZ. This is a path difference compared to AO and BO, comparison of AO reflection and BY reflection. Path difference is equal to XY plus YZ. You can call this as equation 1. But path difference is equal to integral multiple of n lambda. N lambda is equal to XY plus YZ. Let us consider triangle XOY and also ZOY. From these two triangles, we can calculate what is the XY and YZ. See, using the triangle XOY, we have the sine theta is equal to opposite by hypotenuse. That means theta is equal to XY. This is opposite side, and hypotenuse is OY. So XY divided by OY is to be taken as a sine theta, and as I told you, OY is to be taken as a D. So this is sine theta is equal to XY upon D, or XY is equal to D sine theta. Similarly, you can consider ZOY, sine theta for the ZY triangle, YZ upon OY, and sine theta is equal to YZ upon D, then YZ is equal to D sine theta. From equation, we have this n lambda equals to XY plus YZ, and substituting the values of XY and YZ in the equation, we get n lambda is equal to D sine theta plus D sine theta, then that is equal to 2D sine theta is equal to n lambda. So this is called Bragg's equation. And as I told you, where n is the order of diffraction, D is the wave, n lambda is the wavelength, and D is the interplanar distance, and theta is the glancing angle or angle of incident or angle of refraction. So Bragg's equation gives a relationship between the wavelength of X-ray, interplanar distance in the crystal, and angle of reflection from the crystal. And for theta value, you can have this for 0 degree, sin theta value 0, and sin 30 is off, and sin 45 degrees 1 upon root 2, and sin 60 degrees root 3 upon 2, and sin 90 is 1. So this is all regarding the discussion about the study of the derivation of Bragg's law. I hope you might understand all these things very well, and you can attend this question very well at the exam. So next is discussion about the structure of sodium chloride. When you come to the study of the structure of sodium chloride, first we shall draw the figure concerned to the structure of NaCl is as follows. Looking at this figure, this is a nothing but a cubic lattice, but we have FCC structure, face centered cubic lattice. While drawing this one, I have shown here the solid circle as a sodium ion and halo circle as a Cl minus ion. And when looking at these total structure, you can see sodium ion and Cl minus ions present alternatively. This is one unit cell of sodium chloride, where, as you know, this unit cell is nothing but a smallest part of the crystal lattice, which have the systematic pattern of arrangement of the particles in the 3 dimensions. And after having the figure, looking at this figure, say this is a part Cl minus ion, and this is surrounded by other 6 Na plus ion. See, this is 1, this is 2, this is 3, this is 4, and this is 5, and this is 6. That means each Cl minus ion is surrounded by other 6 Na plus ion, and vice versa also. And each ion is surrounded by either 6 opposite charged ions. Na plus is a 6 Cl minus ion, and Cl minus is a 6 Na plus ion. And overall, the coordination number of the each ion in a crystal lattice is found to be 6. The ratio of these two ions are 6:6 ratio. That means 1:1 ratio. So 1 with a 6 Cl minus n and 1 Cl minus a 6 Na plus n. So total it gives a 1:1 ratio. NaCl is being a 1:1 ratio. When you're looking at this further concept, it has a face centered cubic lattice. Na plus is present at the corners and also face centers, while Cl minus are present at the body center and also edge centers. It can also be vice versa. As I told you, every Na plus ion is surrounded by 6 Cl minus ion. Also are having as one above, one below, and one left and one right, one above and these are the already I explained as I told you. Similarly, the Cl minus is surrounded by 6 Na plus ions. We express its saying that Na plus ion as well as Cl minus are the coordination number 6. The structure of NaCl with the coordination 6 is 6. And what would be the unit formula of this sodium chloride crystal lattice? If you look at carefully at the structure of sodium chloride, we shall find that there are 4 units of Na plus and Cl minus, each in a unit cell. Now looking at this total, as I told you, that means this Na plus ions present at the corner and also face center, isn't it? Totally, when you say this a cubic system has 8 corners and FCC, when you have the FCC face centered cubic lattice, that means the FCC has 8 corner particle and 6 face particle. 8 corner particle, 6. The contribution of corner particle to each unit cell is 8 into 1 upon 8 plus contribution of this face center particle per unit cell 6 into 1 upon 2. That is got 8 cancel each other, 2 3 ja, that 1 plus that's got 4. That means when you consider this total simple unit cell of NaCl, where this contribution of sodium plus ions in the unit cell is found to be 4. That is the 4 Na plus ions present in the unit cell. And as I told you, the Cl minus present 1 at the center of the body, 1 at the center of the body, and 12 at the edges of this. These are edges here, edge. So this edge. So edges are there. 12 at the edges of this cubic system. And as I told you, that means if the number of Cl minus per unit cell is equal to 1, that is at the body center, plus the contribution of the edge particle. So 12 into 1 upon 2. 12 is the total number of edge particles of Cl minus, and the contribution of each the particle to the units is 1 upon 4. So 4 3 is 12. So totally, so we have this 1 plus a 4 and 4 Cl minus n. And when you consider this unit cell entire, and it is equal to 4 Na plus ion and 4 Cl minus ion. And totally, when it comes to 4 Na plus 4, the entire this crystal, it is a 4 NaCl molecule present in the unit crystal of sodium chloride. So this, and as I told you, this is being a Cl minus ion and Na plus, all these surrounded throughout the around the Cl minus in the what is the octahedral. So this is the 1 2 3 4, and you have the octal structure. So we have the even outside this plane, every side of the direction of the plane, you can see there is presence of a octahedral structure for these. This is 1 and 4 and 1 above and below. As I told, this is actual structure having the 6 coordination number. So thus we can write this structure of NaCl. The total number of formula units present the 1 unit cell of the sodium chloride is equal to 4. That we can write the 4 NaCl for this. So this is all in the structure of NaCl as such. Now we can write, when you go for attend the examination, you must write the structure and you explain what all the things I have given in the notes is more than sufficient. Okay, thank you. Okay, well.